Introduction. Hello everyone. Welcome back to our electronics tutorial series. In today's video, we have an exciting topic to explore, the half-wave rectifier. This is one of the fundamental electronic circuits that you need to understand in order to dive deeper into the world of electronics. We'll be taking a closer look at its components, analyzing its operation in detail, and visualizing the input and output waveforms using a simulator. So, grab a cup of coffee, sit back, and let's delve into the fascinating world of the half-wave rectifier. Explanation of the circuit. The half-wave rectifier circuit is a simple but essential circuit used to convert alternating current, AC, into pulsating direct current, DC. It consists of a few essential components: a diode, a resistor, and an AC power supply. In our setup, we have a 5-volt, 60 Hz AC supply connected in series with a diode, which is then connected in series with a 640 ohm resistor. This configuration allows us to observe and analyze the behavior of the circuit as we apply the AC input. Diode function. The diode is the heart of the half-wave rectifier circuit. It acts as a one-way valve for electric current, allowing it to flow in only one direction while blocking current flow in the opposite direction. In our case, the diode is forward biased, meaning it allows current to flow when the AC voltage is positive and blocks current flow when the voltage is negative. This characteristic of the diode is crucial for rectifying the AC input and converting it into a pulsating DC output. Waveform visualization. To better understand the behavior of the half-wave rectifier circuit, we have connected a scope to measure and display both the input and output waveforms. The scope provides us with a visual representation of how the voltage and current change over time within the circuit. By observing these waveforms, we can gain valuable insights into the circuit's operation and behavior. Input waveform. Let's focus on the input waveform displayed on the scope. This waveform represents the AC voltage supplied to the half-wave rectifier circuit. Since we are using a 5-volt, 60 Hz AC supply, the input waveform will have a peak value of 5 volts and oscillate at a frequency of 60 Hz. Visually, the input waveform displays a sinusoidal pattern, continuously alternating between positive and negative cycles. Output waveform. Now, let's shift our attention to the output waveform, which represents the voltage across the resistor in the half-wave rectifier circuit. As the AC input passes through the diode, it undergoes rectification. This means that the negative half cycles of the input waveform are eliminated, and only the positive half cycles are allowed to pass through. Consequently, the output waveform exhibits a pulsating DC characteristic. Explanation of pulsating DC. The output waveform appears as a series of positive half cycles separated by zero voltage during the negative half cycles. This pulsating DC waveform represents the rectified output of the half-wave rectifier circuit. However, since we have connected a resistor in series with the diode, the output waveform will also exhibit a voltage drop across the resistor. This voltage drop causes the output waveform to have a reduced peak value compared to the input waveform. The pulsating nature of the output waveform is a result of the alternating flow of current during the positive half cycles of the input waveform. Analysis of current flow. By carefully observing the output waveform on the scope, we can also analyze the current flow through the half-wave rectifier circuit. During the positive half cycles of the input waveform, the diode conducts, allowing current to flow through the diode and the resistor. This creates a corresponding positive half cycle in the output waveform, where the voltage across the resistor is non-zero. The current magnitude is determined by Ohm's law, where V is the voltage across the resistor and R is the resistance value. However, during the negative half cycles of the input waveform, the diode blocks the flow of current. As a result, there is no current flowing through the circuit during these periods, leading to a flat line on the output waveform. This absence of current is reflected as zero voltage across the resistor. Conclusion and applications. So, there you have it, an in-depth exploration of the half-wave rectifier circuit. We've seen how this simple configuration, consisting of a diode, a resistor, and an AC power supply, can convert AC input into pulsating DC output. By analyzing the input and output waveforms, we gain a better understanding of the circuit's behavior and the role played by the diode in rectifying the input voltage. The half-wave rectifier circuit finds applications in various electronic devices and systems. Some common applications include: 1. Power supplies. The half-wave rectifier circuit forms the basis of many power supply circuits, where AC voltage needs to be converted into DC for powering electronic devices. 2. Battery charging. In certain battery charging circuits, a half-wave rectifier can be used to convert AC power into a pulsating DC signal to charge batteries effectively. 3. Signal demodulation. The half-wave rectifier circuit is utilized in radio receivers to demodulate amplitude-modulated AM signals, extracting the original audio or data signals from the carrier wave. 4. Sensor interface. In some sensor applications, where the sensor output is an AC signal, a half-wave rectifier can be used to convert the AC signal into a pulsating DC signal for further processing or measurement. Remember, the half-wave rectifier is just one of the basic rectifier circuits, and there are more complex rectifier circuits like the full-wave rectifier that offer improved performance. However, understanding the half-wave rectifier is a crucial step towards grasping the principles behind rectification in electronics. I hope you found this video informative and enjoyable. If you have any questions or suggestions, please feel free to leave them in the comments below. Thank you for watching, and stay tuned for more exciting electronics tutorials. See you in the next video.